right? So now we can look at one very quick example of data analysis, which is like almost trivial example, right? So what is the trivial example? Let's say in data analysis, what happens is, let's say you are looking at something like this. Let's say you are looking at some price versus some parameters. Okay, so maybe I'll look at let's say this is X, this is Y, and this is price. Okay. Now, what do? I go to the, let's say, the real world. I collect the data and I see what the prices are, and I keep plotting this, right? So whatever, you get some plot like this, right? So typically, this can be modeled by a straight line. Okay, so I have to fit this using a straight line. Okay. What does this boil down to? So essentially, it will boil down to something of this form. Okay, so you need to solve this kind of equations. Do you agree? I don't think I need to motivate this. Y equal to X. Have you seen this kind of equations? Obviously, right? A is, let's say, n cross n. X is n cross 1. Let's say I'll use small letter here. Okay. Y is n cross 1. Right? I want to solve for X. Solve for X. So how do you solve for X? What do you do? Yes? What is it that you will do? How do you solve for X? Huh? Can you tell me? Yes. Yes, yes. What's your name? Ananya. Okay. So can you tell me? Huh? I didn't. Can you shout? Sure. Yeah. No, there is nothing here. So I haven't given you any explicit problem. I'm saying y equal to ax, right? A is a matrix, x is a vector. You're supposed to find what x is, right? I have given you y and I have given you a. So what is it that you will do?
A inverse.
Yeah, you have to find what is called the inverse, right? So what is this A doing? It takes a vector and spits out another vector, right? It's like a transformation. It tells you how to map a vector to a vector, right? You take a vector in Rn, maps it to Rn, right? That's all it's doing, right? So, this is what you have, right? So you have A, which is mapping Rn to Rn. Well, why should one consider such transformation? I can also consider a matrix which is, let's say, n cross m. What do you get? If it is n cross m, it takes a vector in Rm, right? Maps it to Rn, right? So, in other words, how do you generalize this? This is what you have been seeing since high school or maybe PUC, right? Pre-university. But can we generalize this? What is this saying? This is saying how to map a vector to another vector, right? So how do you generalize? What can you say about this R? Let's say Rm. What can you say about this? What can you say about this? This is a vector space, right? What is the dimension of this vector space? M. Okay. This is a vector space. Let me call it as V. What can you say about this? This is another vector space. Let me call it as W. So essentially, this particular matrix A is saying how to map a vector in Rm to a vector in Rn, or a vector in V to vector in W, right? Well, I can generalize this, right? So I can always say, instead of writing A, I'll just write a transformation. Okay, it is a rule or a map, right? Which maps a vector in vector space V to a vector in vector space W, right? Okay. So now, what can you say about Rm and Rn? Suppose I have Rm and I also have Rn. So what can you say about these two relationship wise? Suppose M is 3 and N is 4. What can you say? Let's say R2 versus R3. What is the relationship between the two? What is the relationship? R2 is like all the vectors on a big plane, right? R3 is what? The entire universe, right? So whatever, three-dimensional, right? So now, what is the relationship between the two? See, this is a plane. I mean, R2 is basically a plane. In fact, what we observe is a vertical plane, right? Of infinite size, right? And you have three dimension, and it passes through the origin, okay? And you have three dimension, which is like the entire space. So, what is the relationship between the two? Huh?
Subset.
R R2 lies in R3, right? Do you agree? So R2 itself is a vector space, right? Which sits inside R3. So what is the name that I should give? Subspace, right? R2 is a subspace of R3. Okay. So how do you define that? Okay. So now let me write that as a definition. Let V and W be two vector spaces. Okay. We say that W is a subspace of V if couple of things. If you say W is a subspace, W should be sitting inside V. W is containing V. What is the next thing? W is a vector space. Okay, it's over the same field R. Okay, so or same field F. It should be. I mean, I should be using only real numbers on both. On both are complex, right? Okay. So now this is obvious, right? So this is how one can define. So if I have to show that something is a subspace of another, first thing that I have to show is one is contained in the other, and the second thing is it's a vector space, right? Is there a simpler way? I mean, do we need to show all the properties of a vector space? Suppose I know that this is true. W sits inside V. Should you show that, you know, if I want to show that W is a vector space now, one way is you list out all the properties and verify all the properties, right? It takes time. Is there a simpler way? Remember, W sits inside V. So if you take two vectors in W and add them, it cannot go out of V, right? It should be there in V at least, right? But if you ensure that it's there in W itself, then we are done, right? So we can say that you take any two vectors in W, let U V belongs to W, okay, and alpha 1, alpha 2 belongs to R. You take two numbers. Then if I take linear combination, right, alpha 1 U plus alpha 2 V belongs to W. Okay, if I'll say if, then we say that W is a subspace of V. Okay, so I'll write this. It's a subspace of V here. I mean, it's a subset of V. So first of all, you have to take a W sitting inside V. Now I have to check whether W is a vector space or not. All that I have to do is, if I take any two vectors and linear combination within W, it should be there in W. That's all. The rest assured, right? All the other properties will satisfy simply because of the fact that W sits inside V. Okay? Is that fine? Any questions? Fine, right? Yes. Huh. Huh. No, there is no guarantee that W is a vector space, right? See, what I'm doing is I have a vector space V. V is a vector space. I'm taking a subset W. Now, what will ensure that W is also a vector space? Therefore, it's a subspace, right? One condition that will ensure that W is a vector space is this. No. No, okay, so let me write it one by one. V is a vector space, okay? Somebody has given me a vector space, okay? Second, W is a subset of V. That's also given. Now you ask the question, is W a vector space? The answer is given by take any VU in W, alpha beta in R, then alpha V plus beta U belongs to W. This is enough. Right? If this is satisfied, then W is a vector space, therefore W is a subspace. You understood what a subspace is, right? Clear? Okay. So can you give an example of a subspace apart from trivial one like R3 is a subspace of R4 and R4 is a subspace of R100 and so on? Any other example? Okay, so let's go back to what we did yesterday, right? So one example that we took yesterday was this polynomial, right?